In this lecture, we're going to start our section on the theory of deformation. We're eventually going to get to defining the strain tensor in some of its various forms, take a look at different strain measures. But first, we're going to start off with taking a look at some basic elements of continuum mechanics. Now, there's a few basic things about continuum mechanics that we'll learn along the way. And basically, we need to have a continuous medium. We need to have a material that is not so spread out that it can't be a continuum. Doesn't have to be a solid material necessarily, but it can't be something maybe like a gas that is very low in density. We have other ways of dealing with those types of materials. A couple of the basic tenets of continuum mechanics are that you cannot have one point that separates into 2 points. So we'll not have fracture in this basic version of continuum mechanics that we're going to look at. We can also not have 2 points that collapse themselves into 1 point. Now we'll write all of this down again soon, but I wanted to state that out front. And what I have in this picture are 2 regions. The region on the left we can think of as our initial configuration, and that's supposed to represent a 3-dimensional body. Over on the right is what I'm going to call our final configuration. And in between there may be a sequence of configurations where this shape on the left gets distorted and moved to be the shape over on the right. Now our initial configuration we'll call R, and our final configuration we'll call script R. And we'll have a point P in the initial configuration that gets mapped over to some point script P in the final configuration. I'll show that transformation by this arrow that connects those two, or that line that connects those two. And it's not just that point that gets transformed into that point, but every point does. And all the points in the neighborhood of point P get transformed to points in the neighborhood of script P. Now we call this a transformation from R to script R. We call that a deformation. And so here are a few notes over what we just talked about. Now, there's deformations that we can think of in the traditional sense of things squishing and deforming, but a degenerate type of deformation is just rigid body motion. So let's talk a little bit about rigid body motion first. We'll actually talk about it again after we talk about something called the Jacobian. So there are a couple different types of rigid body motion, rigid body displacements. First of which we can talk about are translations. So if I have a 3-dimensional body and I just pick it up and move it over here, in that case all displacement vectors on the body are the same. So my point over here goes to the point over here, and every point has the same displacement vector, which we're going to call U. Then we have a rigid translation. And the second type of rigid body motion that we can have is a rotation, a rigid rotation. So if I have my same body here again, but I take and I just rotate it, then all the points on that body have the same angle of rotation about the center of their rotation axis. Then we have a rigid rotation. Okay, so those are kind of degenerate deformations. It turns out that any general rigid body motion can be broken up into a translation and a rotation. So we'll call this a pure translation and a pure rotation. And it could be done in either order. You can do the translation and then the rotation, or the rotation and then the translation. You'll end up at the same location at the end, the same configuration of your body. Now in mechanics, we teach an entire class on rigid body displacements, rigid body deformations. Typically, this is an undergraduate class in dynamics. It could be particle dynamics or rigid body dynamics. But in that class, you study the motion of these objects, the ball on the string, and so forth. Well, in our class, we're going to be much more interested in what happens when things deform. So let's set up a little bit a better framework for that situation, and we'll talk about deformations in more general terms. Rigid body displacements will be important for us, but not as important as bodies that can deform and squish as they move around. So we'll go back to our original pictures of the 3D bodies. We have on the left our initial configuration in R, region R with point P. They get transformed into region script R at point script P, and we have the neighborhood of those points. Now we're going to set up initially two coordinate systems. We're going to have a coordinate system x1, x2, x3 in the initial configuration, and then over in the deformed coordinate system xi1, xi2, and xi3. The coordinate system could also be deformed as well. We're going to relax that a little bit. We're going to talk about how we're going to use these coordinates based on the original coordinate system to determine our displacement vectors. But we'll talk about that in a moment. And so we're going to take a look at general transformations. Now the point P in the initial or the reference configuration is going to be located at a point x1, x2, and x3. And in the final configuration, this point script P is going to be located at the point xi1, xi2, and xi3. Now at this point we're going to go ahead and use the same coordinate system for both. So we can draw a position vector to the point P in the initial configuration and another position vector, point script P, in the deformed configuration. So we can think of a vector going from the origin to this point, and the vector going from the origin to that point. And then the difference between those two would be the displacement. And again, the points in the neighborhood of the point transform to the points in the neighborhood of the deformed point. And so every point that has an ordered triple x sub I will transform to a point script p that has an ordered triple xi sub I. Another way to say that is that each point xi sub I is a function of its initial position. And in general, we can think of it also being a function of time. Let's go ahead and write that down. In other words, the final configuration can be described by functions of the initial configuration. So to expand those relationships out just a little bit, we'll do that over here. The location of the point, the xi1 coordinate, would be a function of x1, x2, and x3 in general time. And similarly for the other two coordinates in the deformed configuration. We're going to make an assumption here that there is a one-to-one correspondence between points in R and in script R. And that's part of this idea of the basics of continuum mechanics that says that those 2 points cannot split up, that 1 point cannot split up into 2 points, and that 2 points cannot collapse into 1 point. So as a consequence, then, there's a one-to-one correspondence of points in regular R to script R. And if that's the case, then these functions for xi sub I are invertible. So we could have just as easily said that x1 is a function of xi1, xi2, and xi3 in time, and so forth. Now there are certain fields of mechanics, such as fracture mechanics, where we can loosen some of the restrictions on whether 1 point can split up into 2 points. But in our form of continuum mechanics that we're going to take for now, we're going to be looking at the basics right here. And we'll hold to these basics tenets then of continuum mechanics. And this is something sometimes I'll ask students on a quiz or an exam. What is it about continuum mechanics? What are the basic assumptions? 1 point cannot split into 2 points, and 2 points cannot collapse into 1 point. Now, if we wanted to write field variables or field functions, we can either use the coordinates in the initial configuration or the coordinates in the final configuration. So if we have a field function Q, we can write it in terms of either the material coordinates That would be a function of the original configuration, possibly time, or what we call the spatial coordinates, where Q would be a function of the final configuration. Okay, so you'll see that from time to time written down, either material or spatial coordinates. And to me, it's not as important that you remember which one is the material and which one is the spatial coordinates, but just the understanding that we can write any of our field functions in terms of either the initial or the final configuration. So let's talk a little bit about displacements. So we mentioned how we can position the original body, and we can call that vector x from the origin of the system to that point, and we can position the final body, some point in it, with the vector xi. The displacement then, the displacement vector for that point, will be u. It's going to be the final minus the initial vector. Now we can write these vectors in whatever coordinate system that we want, but if we use our orthonormal unit basis vectors, our E hat I system, we can think of the components as ui E hat I for the displacement, and that would be equal to the xi point in this basis vector E hat I minus our x sub I E hat I over here. Now, given that we're writing this all in terms of the same basis, we can look at the components of the displacement vector. We have the ui would be equal to the xi minus the x components. And that's one way to think of it. The displacement is the final minus the initial position, or sometimes it'll be convenient for us to think of it this way. The final position is going to be equal to the initial position plus the displacement. And that's not anything that we haven't done already. It's just maybe a little bit more formal way of writing it. Alright, well, let's talk about something called the Jacobian. You know, we said that we could take this point that was located at the xi sub I that were functions of x sub I in time, or we can invert these and find the x sub I are functions of the xi in time. And that invertibility also needs to go along with this assumption of the basics of continuum mechanics, and that we need to have relationships that are continuous and differentiable. They kind of go together. If they're not continuous, then we're going to have jumps or splitting, and likewise, if they're not differentiable, we're going to have a hard time dealing with some things. Now, if you've taken a class in advanced calculus, you may have talked about something called the Jacobian to check these relations. So we're going to talk a little bit about that. Going and proving the Jacobian is beyond the scope of this particular course. You may have also heard of the term Jacobian when you take a class in finite elements, and we'll kind of explain how that relates defining elements as well. So let me get a clean page and let's talk a little bit more about the Jacobian. So we have these functions. Xi is a function of x, and I'm going to write down how to evaluate the Jacobian. If we construct a matrix and take the determinant of it, and the matrix would be composed of partial derivatives of each of the xi with respect to each of the x. So for example, the first term would be partial of xi1 with respect to x1, and the remaining entries would be similar. Across each row we'll hold the xi function constant and take the partial derivative of that with respect to x1, x2, and x3 respectively. The second row will be very similar, where we use xi2, take the partial derivative of that with respect to x1, x2, and x3, and then the last one will be xi3 with respect to x1, x2, and x3. Okay, so if we take the determinant, a more simple way to write this would be the determinant of partial of xi I with respect to xj, where I and j are free indices. This is called the Jacobian. And for continuous deformations, j cannot be equal to 0, and for our class we're also going to restrict it to be, it has to be positive. That'd be a consequence of working with a right-handed coordinate system. We've seen something like this previously when we talked about something called the scalar triple product. The scalar triple product of three vectors is formed by taking the determinant of the components of those three vectors. And a similar interpretation can exist for this as we had for our vectors. The volume enclosed by the three vectors is given by the determinant, the scalar triple product. Well, the scalar triple product of these relations says that we can't collapse these deformations, this partial derivative set of invertible relations, we can't collapse those down to zero volume either. So for the neighborhood around point P, that's that other part that we said we can't take a point and split it into 2 points. Well, this says that we can't take a single point and collapse it so that it has absolutely no volume around it. Now in finite elements, where you may see this come about, is if you have a three-dimensional element, you can't collapse that three-dimensional element into a zero volume either. So the Jacobian is a pretty quick check whether or not that is occurring and causes any numerical problems. Now there are a couple different ways to write this Jacobian. In this form I have the partial derivatives of xi with respect to x, but we could also write this in terms of displacement. Now if you recall from the other page, we said that the final position was equal to the initial position plus the displacement. So if we evaluate this partial derivative here, we can say it's the partial derivative of xi with respect to xj plus the partial derivative of ui with respect to xj. Now this first term we've actually seen before, and that's going to be the Kronecker delta. So obviously if we take the partial derivative of x1 with respect to x1, then that will equal to 1. If we take the partial derivative of x1 with respect to x2, then that will be equal to 0. So that is our Kronecker delta. And then we have this partial of ui with respect to xj. Now at this point I'm also going to introduce another type of notation. I don't think we've seen this yet, and that is the comma to denote a partial derivative. So a lot of times in books and in papers you might also see this notation, ui comma j. And that comma denotes a partial derivative with respect to the spatial coordinate. So in matrix form, we can write this a little bit differently. In our first entry, when I is 1 and j is 1, the entry here will be Kronecker delta 1, 1, which is 1, plus the partial derivative of u1 with respect to x1. The second entry, where I and j are not equal, that'll just be the partial derivative of u2 with respect to x2, u1 with respect to x2. It's easy to get mixed up on these subscripts. And then the third entry will be the partial derivative of u1 with respect to x3. And I'm going to go ahead and complete this. But I want you to notice that we have 1 plus this partial derivative along the diagonal, but only on the diagonal. Now for some of your homework, you're going to be evaluating the Jacobian. Sometimes they will give you the functions in terms of xi. Sometimes they will give you the displacement. From a measurement point of view, it's often a little bit easier to measure displacement necessarily than it is the final position, or you may just be given the displacement vectors. And so don't forget to put that 1 on the diagonal for the displacement. It's very common that I'll see students mess that up. So let's make a little note of that. And there we have it. Well, we'll take a look at more sophisticated, some fairly sophisticated deformations as we go through the class. But we've talked about one degenerate form of a deformation called a rigid body motion. So let's see what would happen to our Jacobian when we have a rigid body motion. Alright, so let's take a look at rigid displacements again. Here we have our Jacobian written in terms of displacement. And if this is my region regular R, well, I guess the most degenerate form of a rigid deformation would be absolutely no displacement at all. At time 1, the body is sitting there, and at time 2 it hasn't moved, and it still sits right there. So we have absolutely no movement, and every point xi sub I is just exactly equal to every point x sub I. We have no displacement. All of our u sub I is equal to 0. Well, in that case, it's pretty easy to calculate our Jacobian. We have 1 plus the partial derivative of u1 with respect to x1. Well, that's 0. And so are all the other partial derivative terms. So we end up with 1s along the diagonal and 0s everywhere else. The Jacobian in this case is equal to 1. Now we talked about how the Jacobian, or the scalar triple product, is sort of a volume measure, and if this holds for every single point in the body, then what this is saying is that the volume of this body hasn't changed. We can even make this a little bit more interesting. We could say that each of these is a constant. Each of these displacements are a constant. We'd still end up with a Jacobian equal to 1. And again, so we can see again that as the volume changes, the Jacobian is going to change, and this is a local measure. It's not for the entire body, but for a particular point in that body. But if the body is rigid, then this will hold for all the points in the body as well. So you can imagine situations where maybe you have a ball and it has a certain size to it, and you expand that sphere. Okay, then you can use the Jacobian as a volume measure for the points in that sphere. The change in the volume. So you can think of things doubling in size or getting half as big, and you can have an appropriate calculation for the Jacobian in that way as well. Alright, well, what we're getting ready to do then is to take a look in more detail about things that deform on the surface and in the interior of a three-dimensional body. And in this next section that we'll do in the next video, we're going to go through the details of the extension and a rotation of line segments in the body. We're going to use a lot of our index notation. So if you haven't been as familiar with it, please go back and review some of our previous videos on index notation. So we'll get into that and use that quite extensively.